Okay. Now, part 4, lecture 7, the importance of the constant of motion. It's very, very important. So, the constant of motion plays an important role in Hamiltonian dynamics. 1. Predictability and conservation laws. Constant of motion correspond to conserved quantities: energy, momentum, angular momentum, and so on. These conserved quantities are rooted in the symmetries of the system via Noether's theorem. This you'll see later, okay, ahead. Now, this is number 1, this is number 2, reduction of complexity. Each independent constant of motion reduces the effective number of degrees of freedom. Now, if you have n degrees of freedom and k independent constant of the motion, you may simplify the system to effectively n minus k variables. You see, that's an important application of the constant of motion. Now, number 3, integrability. A Hamiltonian system is called integrable if it has as many independent constants of motion as degrees of freedom. So, constant motion and degrees of freedom, they are close together. So, knowing enough constants of motion allow us to sometimes, not always, sometimes solve the equations of motion exactly. You see, that's the importance of constant of motion. And finally, number 4, a symplectic structure preservation. Constant of motion help maintain the structure of phase space. Attention, of phase space is contains the independent variables q, coordinates, generalized coordinates, and p, the generalized momentum. So that's what we call phase space or cotangent space. You see? Now, volume preservation via Liouville's theorem. This you'll see later. They ensure that the motion stays confined to certain surface, these level sets, in the phase space, like energy surface and so on. Thus, you see, that's a definition of constant of motion. You see, the Poisson bracket F and H plus this partial F respect to T reviews conservation laws, simplifies dynamics, ensure integrability, preserves phase space structure. That's a summary of 1, 2, 3, and 4. Now, finally, I will present only the definition. Okay, I will not go through. You see, just a definition. What is symmetry? Attention now. Symmetry, the definition applies to classical physics and classical mechanics, this case, and also particularly to the Hamiltonian system. You see, not only classical mechanics and physics. So, a symmetry, attention now, that's a definition, is a transformation that leaves the physical laws of the Hamiltonian unchangeable. You see, that's the definition. You see, you have a set of variables. If you change the variables, you see, the physical laws, okay, unchanged. That's the definition of symmetry. I'll repeat. You have a set of variables, in this case, you have generalized coordinates, and then the momenta, generalized momenta. You see pi and qi and pi. So if you adopt, you see, a transformation to other set of variables, the physical law remain unchanged. That's the definition of symmetry. You see? Then we will develop this, the consequence of this definition. Okay? That's very important.